Formal proofs in Heilbronn logic are similar to formal proofs in propositional logic. The main difference is that there are additional mechanisms for dealing with quantified sentences. In the Fitch system for Heilbronn logic, we include all 10 of the rules of inference for propositional logic. We have negation and introduction and negation elimination, implication introduction, implication elimination, biconditional introduction, biconditional elimination, and we have introduction and elimination rules for both conjunctions and disjunctions. In addition to these logical rules of inference for logical operators, we have 4 new rules of inference for quantified sentences, introduction and elimination rules for both universal and existential sentences. Let's look at these in turn. Now, if you're like me, the prospect of going through a discussion of 4 rules of inference sounds a little bit repetitive and boring. However, it's not so bad. Each of the rules has its own quirks and idiosyncrasies, its own personality, if you will. In fact, a couple of the rules suffer from what I might characterize as a distinct excess of personality. For we to use the rules correctly, however, we need to understand these little idiosyncrasies. Universal introduction, or UI, allows us to reason from arbitrary sentences to universally quantified versions of these sentences, subject to a constraint that we're going to discuss shortly. Typically, UI is used on sentences with free variables to make their quantification explicit. For example, if we have the sentence, hates Jane X, then we can infer, for all X hates Jane X. Note that we can also apply the rule to sentences that do not contain the variable that's quantified in the conclusion. For example, from the sentence, hates Jane Jill, we can infer, for all X hates Jane Jill. And from the sentence, hates Jane Y, we can infer, for all X hates Jane Y. These are not particularly sensible conclusions. However, the results are correct, and the deduction of such results is necessary to ensure that our proof system is complete. Now, there's one important restriction on the use of universal introduction. If the variable being quantified appears in the sentence being quantified, it must not appear free in any active assumption. That is, an assumption in the current subproof or any superproof of that subproof. For example, if there's a subproof with assumption P of x, and from that we have somehow managed to derive Q of x, then we cannot just simply write for all x Q of x. If we want to quantify a sentence in this situation, we must first use implication introduction to discharge the assumption, and then we can apply UI. In the example here, we first apply implication introduction to derive the result P of x implies Q of x in the parent of the subproof containing our assumption, and then we apply universal introduction to derive for all x P of x implies Q of x. Our second rule of inference is universal elimination, or UE. Universal elimination allows us to reason from the general to the particular. It states that whenever we believe a universally quantified sentence, we can infer a version of the target of that sentence in which the universally quantified variable is replaced by an appropriate term. I'll explain this condition in a minute, but first some examples. Consider the sentence, for all x hates Jane X. Jane hates everyone. From this premise, we can infer that Jane hates Jill. We can also infer that Jane hates her mother. And we can even infer that Jane hates herself. In addition, we can use universal elimination to create conclusions with free variables. For example, we can infer hates Jane X, or equivalently, hates Jane Y. In using universal elimination, we have to be careful, though, to avoid conflicts with other variables and quantifiers in the quantified sentence. This is the reason for that constraint on the replacement term that we saw earlier. Consider the sentence, for all x, there exists a y, hates xy. In other words, everybody hates somebody. From this sentence, it makes sense to infer there exists a y such that hates Jane Y. In other words, Jane hates somebody. However, we do not want to infer there exists a y hates y. In other words, there's somebody who hates herself. The problem here is that the quantifier in the sentence has captured the variable being substituted. and we need to avoid this. Let's formalize this notion of capture. An occurrence of a variable nu in an expression phi captures a term tau if and only if tau contains a variable mu and the occurrence of nu lies in the scope of a quantifier of mu. What? That's a fairly complicated definition. Fortunately, it's really easy to understand via an example. Suppose you want to substitute mother of x for y and there exists an x hates xy. We cannot because the occurrence of y in there exists an x hates xy captures mother of x. Why? Because mother of x contains a variable x and the occurrence of y lies in the scope of a quantifier of x. What follows, we say that a term is substitutable for a variable nu in phi if and only if there's no free occurrence of nu that captures tau. Some texts say that tau is free for nu in phi. Let's look at some examples. Mother of Jane is free for y and hates Jane y, since the term contains no variables at all. The term mother of x contains variables, but it's free for y and hates Jane y, since there are no quantifiers. The term mother of x is free for y and there exists an x hates zy, because it does not contain a variable that is quantified. Here's a tricky case. The term mother of x is not free for y, and there exists x hates xy, because there is an occurrence of y in the sentence that lies within the scope of a variable contained in mother of x. And finally, mother of x is free for y in this complex sentence here at the bottom. Although there's a quantifier of x in the sentence, it's okay because the only free occurrence of y lies outside the scope of this quantifier. Avoiding conflicts of this sort is the main reason for the substitutability condition in the definition of universal elimination. When using the rule, if we obey the law, we won't get into trouble. Existential introduction's easy. Not much personality here. If we believe a sentence involving a ground term tau, then we can infer an existentially quantified sentence in which one, some, or all occurrences of tau have been replaced by the quantified variable, with the assumption that tau does not occur in phi. For example, from the sentence hates Jill Jill, we can infer that there is someone who hates herself. There exists x hates xx. We can also infer that there is someone Jill hates. In other words, there exists x hates Jill x, and there's someone who hates Jill. In other words, there exists x hates x Jill. And by two applications of existential introduction, we can infer that someone hates someone. There exists x, there exists y, hates xy. Note, however, that it's important in existential introduction to avoid variables that appear in the sentence being quantified. Without this restriction, starting from there exists x hates Jane x, we might deduce there exists an x such that there exists an x hates xx. It's a kind of odd sentence since it contains nested quantifiers of the same variable. However, it's a legal sentence and it states that there is someone who hates herself, which does not follow from the premise in this case. Finally, existential elimination. Suppose we have an existentially quantified sentence with scope phi, and suppose we have a universally quantified implication in which the antecedent is the same as the scope of our existentially quantified sentence, and the conclusion does not contain any occurrence of the quantified variable. Then we can use existential elimination to infer the consequent. For example, if we have the sentence there exists x hates Jane x, and we have the sentence for all x hates Jane x implies not nice of Jane, then we can conclude not nice of Jane using one application of existential elimination.